All right, hello, welcome back everyone to Complex Differential Geometry. Last time we were in the middle of lecture 6 and we had just complexified our differential forms. So we were looking at complex differential forms. I actually forgot, well, I in fact started talking about, let me see, where do I want to write this? Complex exterior forms. So we had this space lambda pq of t star m. So that was the space of, let me see if I got that right. Yeah, so that was the space of complex exterior forms. So I forgot to mention that when we go to complex differential forms, this is going to become omega pq of t star m. There should probably be a p here. No, this is the bundle. So this is the bundle. So this is the complex exterior form bundle. That's the point that we got to. And then if we take a smooth section, then we get this space. This is actually the space of complex differential forms. Differential PQ forms, to be exact. Oh, well, before we start, so I just wanted to get all of that cleared up. And so now let's do a brief recap of what we did last time before we get into the next part. I'm going to try to keep this very short. So number one, we talked about tensor algebras. Which were the sums of all the RS type tensors, the space of the sums of all RS type tensors with the tensor product as their multiplication, tensor product. Then we took the projection onto the antisymmetric part, and we considered a single grade plus k grade. That gave us the kth exterior algebra. Also keep forgetting to mention that the product would be the exterior product. Exterior product. And if we merge all of the kth exterior algebras up to the dimension of the space, then we get just the exterior form algebra. And here we get this idea of exterior k-forms. Well, I suppose you would get it from here. So exterior k-forms. And the way you read this is just, this is a antisymmetric 0k tensor. Will become a 0k tensor field when we go to the smooth section. So number 3, we then went to the bundle. We went to the bundle, or we defined the bundle of lambda k tp star m, which was lambda k t star m, and then we took a smooth section of that. So then we took a smooth section of this bundle, and that gave us omega k of t star m. this is now a real exterior differential K-form. And then we complexified it. So you might call this omega C if you'd like. You might drop the C if it's implied that we're working in the complex field. So this is, by definition, omega K T star M, real direct product with the complex numbers. And so these are the same thing, but instead of the scalar multiplication being on the real numbers, the scalar multiplication will be on the scalars will be complex. So there you go. And that's the last thing that we did. And then I clarified that, oh, and then lastly, we split it, right? We also, at the end, we split our K-forms into PQ forms using the result that V star cross C is isomorphic to V star 1, 0, the holomorphic forms, holomorphic 1 forms, plus V star 0, 1, the anti-holomorphic 1 forms. Holomorphic, I'm gonna write this in short, anti-holomorphic 1 forms. So that's what we did so far. And now there's an interesting thing. We also defined the exterior derivative. Exterior derivative. And that's where we're going to start now, is we're going to talk about the exterior derivative. This was a map that went from omega k to, well, omega k on M to omega k plus 1. So if I give you a differential k form, then the exterior derivative would give me an exterior differential k plus 1 form. And subject to some properties, the Leibniz rule, the distributivity. Let me go back and check. Oh, right, that it squares to 0, d square is equal to 0, and that df of if f is in the omega 0, then it's just the differential of a map. So that's where we left off from. The first things first, so we've already split the space of differential forms into the holomorphic part and the anti-holomorphic part. So now we'll see what that does to D. So splitting the exterior derivative. And what I'd like to remind people in this lecture, so far we've been working on an almost complex manifold. So M is right now an almost complex manifold. And we don't know if J twiddle is integrable. So that's what we're going into here. And then later on, we're going to impose the fact that J twiddle will be integrable, and we'll see what happens when we do that. So let's see what happens when we take, let's say this is a K form, and we send it by the exterior derivative to its derivative d alpha. So we're sending alpha to d alpha. What happens? The proposition is that d alpha is an element So okay, so not just a K form, but a PQ form. PQ form. So we're going to say that d alpha is an element of omega p plus 1 q of m. Let me skip the m's here. I mean, it's implied and it's not very important to the point. Just remember that there are going to be a bunch of m's here. Let me write the main part, which is p q plus 1 p minus 1 q plus 2 and the last one, which is omega p plus 2 q minus 1. So notice that d has to send omega k to omega k plus 1, right? It increases the degree of the form by 1. So notice that with all of these, the overall, so the degree k, right, is k is equal to p plus q for a pq form. So where we have to overall add 1. Um, so this also adds to p. Every sum has to be p plus q plus 1. And you can see this is also p plus q plus 1. This is also p plus q plus 1. But the interesting thing is that there are way more ways to make p plus q plus 1, especially if we have access to, if we're allowed to subtract as well as add, right? So why aren't there any more terms here? And we'll get into exactly why. So let's provide, this is going to be a bit of a heuristic proof. But it should get the point across. So let's say that we have omega, which is a PQ. Well, in fact, okay, let's stick to omega. I'll rename this to omega because translating it on the fly is going to be difficult. So let's call it omega. So let's say that omega is f wedge d theta wedge d phi. And what we're going to say is that this is a smooth function. So you can think of this as our, so this is on C infinity m. You can think of this as the coefficient in front, and have a different color here. So this is a holomorphic P form, and get a different color. So, and this is an anti-holomorphic Q form, which makes omega overall would make this a PQ form. Remember, at this point, whenever I say form, I mean exterior differential form. We're no longer going to be talking about just exterior forms or any of those things. From now on, it's always going to be a differential form. So the first thing that we're going to do is that we're going to differentiate it, right? So we're going to apply the derivative. So let's see, what is d omega? So d omega, we have to use the Leibniz rule. So this is equal to df wedge d theta wedge d phi, and plus d, so f wedge d of d theta wedge d phi. Did I do this wrong? Oh, sorry, I missed this. So these were not already supposed to be one form. So yeah. So yeah, let me correct that. So we have something like this. The reason I caught that was because we weren't supposed to delete all of those terms. So anywho, f wedge d theta wedge phi plus f wedge theta wedge d phi. So now what do we do? We're going to analyze these terms. So let's zoom in to one of these terms. We're going to zoom into which one? Oh, we're going to zoom in right into one of these terms. So we look at this d theta, then that's equal to d of, so theta is a p form, right? So let's decompose it into a bunch of 1 forms. It'll look like that. And so then this, we have to apply the product rule again. So this is d theta 1 wedge dot 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 wedge theta p plus dot 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 plus theta 1 wedge dot 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 wedge d theta p. Right. So what could happen to this to these individual d theta 1? So theta 1 was a 1 form, right? So in the complex sense, in the PQ grading sense, this 1 form could become any 2 form, right? Any 2 form. So what we're doing is we're losing a 1 form and we're gaining a 2 form. There are a few different kinds of 2 forms that we could get from this, depending on what kind of 1 form theta 1 is. And so we could get a 2, 0 form. We could get a 1, 1 form. We could get a 0, 2 form. So so then what would happen? I mean, what we're trying to do here, if to zoom out a little bit and to give a little bit of a bigger picture, what we're trying to do is trying to figure out what, again, which of these spaces that they're going to inhabit. So we need to figure out what grades these terms are going to be. So these are the grades of the new terms, and we're going to lose a term that is going to be a 1, 0 form, right? Because we already said that this is a holomorphic form. So this is going to be, if this is a holomorphic P0 form, or this is a P0 form, then this is a 1, 0 form. So what kind of grades are we going to get? We're going to get 2, 0 minus 1, 0, which is equal to plus 1, 0. So this is going to give us a P plus 1 Q form. So this is the delta, right? This is the change. So, or let me just say that's the change. So overall, this is going to give us a P plus 1 Q term. And then if we have a 1, 1 form, then if we subtract off the 1, 0, so we're losing a 1, 0 form. We're gaining a 1, 1 form. That's why we're doing this. So that gives us 0 plus 1, right? So that gives us, and do it in a different color so that we don't get too bogged down here. So that will be a P Q plus 1 form. Okay, so we already have terms that look like this and terms that look like this, right? So secondly, we have, or lastly, we have 0, 2 minus 1, 0. That will give us a minus 1 plus 2 form, or a change of -1 and +2 to the grading. So this will give us p minus 1 q plus 2. And if you repeat this for the phi term, right? So this one, then what we'll see is that we have phi 1, we'll look at d phi 1, a 0, 1 form, and then this 0, 1 form could become a 2, 0 form, a 1, 1 form, and a 0, 2 form. And if we subtract these with that, then we'll find that overall we get a p plus 1 q form, a q p plus, a p q plus 1 form, can't really change interchange them, and we'll get something that looks like this one but a little different. We will get a p minus 1 q plus 2 form. I think that's the other one, right? No, that's the same one. The one we will get here is p plus 2 q minus 1. You can do the math yourself, and because this is 0, 1 instead of 1, 0, that's why we'll get these three combinations. And so let me kind of give a brief justification for why, and this will happen for all of these, right? So this will give us an extra form, and so all of these terms will have a similar, because each of them have one exterior derivative, these will all give us a similar addition of grades. So because we, it's fundamentally because of this. So one form is going to a 2 form, right? There are no three forms being made. So the only other way to make p plus q plus 1 is to have like a +3 and a -2, right? But where are we going to get a +3 from? We can't get a +3 because the differential, the exterior derivative is not going to give us a +3. So that's why we're limited to these terms. On an almost complex manifold, d omega will have these terms. So you can like, the reason why this is a heuristic proof is obviously we didn't go term by term and make sure that every single term is like this. But what I'm claiming, and what you can check if you are really inclined to do so, is that there are no other different changes in grade. So if we think of, okay, well, there are no other changes in grade, if every term gets a grade change that is within all of these, then definitely d omega has to be in an element of this space, and it can't be anything else. We would have to show that there's a different term in there. So that, even though I didn't show all of the terms, I think you can get a pretty good idea that this is the whole space that is going to exist. And that is pretty much guaranteed by the fact that when you think about the fact that one forms can only become two forms. Okay. But if I had just said that one forms become two forms, it might not have been convincing. So I did some of it. I did some of the calculations. Okay. So what did we learn? We learned that on a complex, on an almost complex manifold, d omega to d omega is an element. So if this is a pq form, then d omega must be an element of pq plus 1 plus omega p plus 1 q plus omega p minus 1 q plus 2 plus, lastly, p plus 2, I don't know why I have so much trouble writing the last one, q minus 1. So that's what we have on an almost complex manifold. So what happens when J twiddle is integrable? If J twiddle is integrable, then we have actually a complex manifold, right? That's what we figured out in lecture 5. So let's decompose D in, well, we weren't really able to decompose D in this manifold yet, right? There's something that you could do. You'd have like some operator D P Q plus 1 plus D uh, P plus 1 Q plus D P minus 1, etc., etc. I'm not going to write the whole thing. You could see that there would be a decomposition of some sort. Um, it's maybe not very popular. What's more popular is what we get for a complex manifold. So D on a complex manifold is what we're going to look at next. And as we hinted or outright said last time, is that on a complex manifold, D attains this really, what am I writing? D attains this really nice form where I call this partial and partial bar. So these are the Dolbeau. Let's see if I can spell Dolbeau correctly the first time this time. Dolbeau operators. And that comes from the idea that when we do this process, or when we carry out this process on a complex manifold, what we get is that d omega is an element of omega p plus 1 q plus omega p q plus 1 and nothing else. So plus, well, I don't know how to say that. So let me just say it in words. And nothing else. So let's show that this is indeed the case, and let's construct these operators. So first of all, we will say, yeah, we will have to show this thing that the action of D is inside here. So we know that in general it's in this. We know that it has to be in this set because every almost complex manifold, every ACM is a complex manifold, right? So we know that it's at least must be in this space. So we can start off with that. And then our task will be to show that there are no components. Oh, well. There are no components in these spaces. Okay. So let's do it. Okay. We're going to introduce something called multi-index notation. I haven't used this before in this lecture series, so I'll briefly go over how it works. We're going to use these things called multi-indices. I is equal to I1 dot 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 IP, and J is equal to J1 dot 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 JQ. And when I write something like omega I, that means that you have to think of this as there is an omega I for every one of these. So there's like an omega I1, there's an omega I2, whether like it might be a sum, it might be a product. So you'll have to think that there's a term for each one of these. And so I'm going to write something like this. Omega ij, so these are labels, so these are going to be coefficients. And then you have dzi, dz bar, j. So here in this product, there's actually many terms, right? So there's like an omega I1, J1, dz1, I1, dz bar, J1. And then like for every combination of pairs of something from this set and something from this set. That's how you read this notation. Okay, so that's multi-index notation. Multi-index index notation. That's just a little refresher from tensor algebra. When you get really, really large tensors and you need many indices, it's customary to use multi-index notation, which is what we're doing. We have very large covariant tensors right now. So let's take the derivative of omega. So then that gives us d of omega ij dzi wedge. Oh, I didn't put the wedge here. So wedge dz bar j. Okay. I just noticed something. Maybe I'll address it in a little bit. So hello, editing Saif here. So I just noticed that I forgot to mention that little error that I was referring to in the live session. So what it actually comes down to is that I'm pretty sure this wedge product isn't supposed to be here. This C infinity function just lives in front of this differential form as a coefficient. So you have this P form, holomorphic P form, and you have the anti-holomorphic Q form over here, and they're wedged together, and the coefficient is out in front. You can contrast that, or you can compare and contrast that to the PQ form that I wrote there, which was dz I wedge dz bar j. So that's the mistake I was thinking of correcting. I didn't end up getting to it, so hopefully that makes sense. Once we differentiate it, we still get the same thing. So everything else is fine. Okay. The next thing is obviously we have to distribute this. So then first thing we get is omega d omega I j. So this is our coefficient, right? So this is from C infinity m, and so then we get something like this: dz I wedge dz bar j. Then you get another term. I'm just going to write it like this. We get d or omega I comma j d of dz I wedge dz j. And this is going to be 0. This is going to be 0 for a very subtle point. In fact, I made this mistake first when I was writing the lecture notes. So I thought that this was 0 because d squared is equal to 0. But d squared this is not the right reason for this being 0. And the reason for that is very subtle. So we have dzi and dz bar j are the basis, like the basis covectors here, or one forms, the basis one forms. But even though we're calling them dzi, this is just a name. You can think of it as like dz is the name. It's not, like there's a pun here. There is the operator d acting on z, or zi, and there is this thing that we call dzi. And unless our coordinates are holomorphic, so this is where j being integrable comes in. If j isn't integrable, then these are not the same thing. Because the holomorphic coordinates, or the holomorphic tangent bundle and the anti-holomorphic tangent bundle, don't actually close to form to form coordinates. So the coordinates are not the same thing as the exterior derivative. Well, this is the exterior derivative of the coordinates. Exterior derivative of the coordinate functions. If the atlas is not holomorphic, then this is not equal to these things, and therefore this is not 0. Because why would it not be 0? Because we know that d after d of some function is 0. But if this is not equal to d of some function, then there's no reason to use um, this constraint, right, or this rule for the exterior derivative. So the reason that this is 0 is because of holomorphic coordinates. I hope that point is clear. This is because we have holomorphic coordinates, which is why I was wondering whether or not to introduce this term so early. We've already talked about the closing of the vector fields and so forth. So let me just briefly like mention this and say that we're going to talk about this later on when we talk about cohomology. Where if d after d, or if d of some vector or some form is 0, this is called a closed form. And sorry, if our dzis may or may not be closed forms on an ACM, but on a complex manifold, they always close. So let me take a moment here to say a few things that are equivalent to each other. So nj twiddle equals to 0 is equivalent to the existence of a holomorphic chart. We already showed that. Or sorry, I keep calling it a holomorphic chart. A holomorphic atlas. Holomorphic atlas. But it's also equivalent to the closed, the coordinate one forms being closed. And therefore, this is 0. So we only have to worry about this term. All of that hullabaloo just to say that we only have to worry about this term. And in fact, what you can think of this as is that this is the term where the p minus 1, q plus 2, and p plus 2, q minus 1 terms are going to come from. And so because this is 0, we're not going to get those terms. So let's see what happens. So we're going to show this explicitly. This is not going to be heuristic. So let's continue. Sorry about that. Let's continue decomposing this. So now we have just this term, d omega ij wedge dz I wedge dz bar j. So then on a function, this is just the differential of the map, right? And we can go back to lecture 1 to remember what the differential of a smooth function is supposed to be. So this is just going to be omega ij. It's just the based on the directional derivative, right? So let's write the form of the directional derivative. Also known as, or also like very similar to the chain rule. So there we go, dz bar k, and then we wedge all of the usual suspects here, dz bar j, and then that's equal to, now let's just distribute it over, right? Let's just distribute all of the terms to see what we got. dz bar j plus partial omega ij partial z bar k dz bar k wedge dz I wedge dz bar j. So what rank forms are these? Well, this is just a coefficient, right? This is just for our case, this is just a number as when we're considering it. So um, well, technically it's a smooth function, but for it's still a coefficient because we're working on, if we were working at a point, it would be a number. Since we're working over the entire manifold, it's a smooth function. So what we really care about is this part. So remember that we're working with holomorphic coordinates now, and so this must be a 1-0 form, right? There's nothing else it could be. And this has to be a 0-1 form. This has to be anti-holomorphic. So we add, we're adding a 1-0 form and a 0-1 form. So that gives us overall right? This is the delta. This is actually the delta that we were working with, the change. So this is our overall change in this whole thing. This is what we already had. So this is the change. So then if this, since this is a PQ form, so then the whole thing is, so this is our P plus 1 Q form, and this is our P Q plus 1 form. Therefore, D is D of omega is an element of omega P Q plus 1. So here we've actually checked every term, right? We didn't skip over any term. So this is completely rigorous. So this is I keep wanting to write Q in the first slot. P plus 1 Q. Right. And then there's an M here. Maybe let's put that there for once. So okay, we've proven that. And this wouldn't work. This wouldn't work is precisely when that other term would not be 0, right? If we couldn't say this, dz I wedge, sorry, that's not a bar. This is dz I wedge dz bar j. This would not be 0 if this was not, if these were not closed forms. This was not closed, then this would not be equal to 0. And so then on an almost complex manifold, you couldn't do this. I want to make it very clear. It's something that we can't do on an almost complex manifold in general. But if the almost complex manifold has an integrable J twiddle, then we'll be able to do this, because an integrable J twiddle is equivalent to holomorphic coordinates. Holomorphic coordinates is equivalent to dzi being closed. Okay. Step two of the proof is, because we've so far shown that D is in fact inside this space, that should be a circle plus. It's in fact in this space. So we can say that D of omega is equal to partial, so we define it this way, partial of omega plus partial bar of omega, where this is an element of omega P plus 1 Q, and this is an element of omega P Q plus 1. There, got that one first try. So where we can define these as partial is defined to be a projection operator, P plus 1 Q after D. So we project the D operator down to the P plus 1 Q space. So this is an omega PQ going to an omega P P plus 1 Q. What am I trying to say here? In fact, let me say it a different way. So PQ, then I wanted to put the thing that we get in the middle, right? So we go to so this is D. Let me write it this way. Kind of coming up with this explanation on the fly, so bear with me. So PQ, D will take it to P plus 1 Q plus omega P Q plus 1, right? And then pi P plus 1 Q will then project only one of the spaces. So it'll just take this and just cut it out. And so then we'll get omega P plus 1 Q. That's our idea here. And yeah, let's put that back in here. And obviously, partial bar is the same thing, but we're projecting it into the other space, P Q plus 1 after D. So that's how we get this. This is how it works. This is how the operators are equal to each other. If you were to use D on a PQ form, then it would decompose like this. So that is our definition. We then have to show that it follows all the rules, right? So step 3, it inherits the Leibniz rule, from D. So because this is just a direct product, we can and because Leibniz rule distributes over the addition, right? So we can just have a separate Leibniz rule for this and a separate Leibniz rule for that. It's the exact same one as the one for D. So yeah, partial of, I'm going to only write the one for partial. The one for partial bar will be the same thing. Alpha wedge beta is going to be partial of alpha. So this thing as its own thing, partial, and then wedge beta plus minus 1. Literally the same thing. We're just inheriting it from the space, the super space. So, and then, right. So that's our Leibniz rule. And there's one for partial bar. And now, in order to fully define it, because we can keep using the Leibniz rule to decompose until we have the partial of an zero form, right? So how do we deal with a zero form? So zero form. So partial f is defined as partial f partial zj. Keep in mind the Einstein summation convention here. And partial bar f is defined as partial f partial z j dz bar j. And there is, remember, I want to keep bringing this idea back up that we're using coordinates here, right? Coordinates. And you have to be very careful when you define something using coordinates, because coordinates are not real. And they're not complex either. They just don't exist in a certain sense, even more than the rest of the math. So we have to make sure that this is coordinate independent. And it is, it will be coordinate independent as long as, I'm not going to get into the working out of this, but just trust me on this one. As long as we have holomorphic transition maps. So yeah, if you could transfer this to another local coordinate wj, and then you'd find, or wk, let's say, and you'd find that it would have the same form there. So this is well defined. So that's the last thing to do. And now we would like to show some properties. Properties of uh, you know, partial and partial bar. So we know that d squared is equal to 0, right? Which is actually saying that d after d is the same thing as the 0 map. So, well, this is also the 0 map. This is not the number 0, it's the map that sends everything to 0. Because this is a map, then this has to be a map. Sometimes I think people forget that, so I just wanted to mention. So, let's say that d squared is equal to 0. This implies that partial plus partial bar square is equal to 0. And we can then expand out this as an operator. And if we do that, what we'll get is that partial square plus the mixed terms are going to, we can't assume that they're commutative. So we're going to write it like this: partial partial bar plus partial bar partial. And then you get partial bar squared, which is equal to 0. But notice that these are all operators that act on different spaces. This one acts on, or this one sends everything to omega p plus 2 q, right? Two applications of partial. This one sends everything to omega p q plus 2, and both and these ones send to omega p plus 1 q plus 1, right? Both of them. And so just like how when you have a polynomial, I keep using this analogy. So let's say that you have bx plus c is equal to 0. These are all linearly independent, right? So for it to be 0 for every choice of x, a and b and c would all have to be separately 0 because these are linearly independent. And so there's a similar idea going on here, because these are all sending whatever, like you can think of this as like partial square of omega plus partial partial bar plus partial bar partial plus partial bar squared. Sorry, partial bar squared of omega is equal to 0 of omega. Again, 0 is a map. So each of these, because they're in a separate space, in order for them to all be identically equal to, like their addition to be equal to 0, they have to individually be 0. So this is 0, this is 0, and this is 0. So then we get 3 new properties. Partial squared is equal to 0. Partial bar squared is equal to 0. And an extra one, which is that partial bar plus partial bar partial is also equal to 0. These are 3 important properties of these new operators. Properties of Dolbeault operators. So this is one of our big results. So this is something that we're going to use in Dolbeault cohomology. Just like d squared is equal to 0 is important to DRAM cohomology. And DRAM cohomology is the real version of Dolbeault cohomology. So yeah, and the analog of this to the complex case is these 3. It gets more complicated because instead of just having k forms, right? Instead of just having k forms, we now have pq forms. And so that's why these become a little bit more complicated. So where p plus q is equal to k, right? Uh, but this is what gives us a lot of power. Um, for the restriction is what makes a lot of structure emerge from complex spaces. So that is our last um, result. Now let's just see what uh, kind of take stock of what we just defined, the Dolbeau operators. Dolbeau operators is this part is you might say it's a bit redundant, but given that we were deriving the Dolbeau operators as a consequence of just looking at what uh, how D would act on a complex manifold. um, Remember I was saying that um, that D had a particularly simple decomposition for uh, in the complex case, or the PQ decomposition becomes particularly elegant. That's what I was saying, is that D is equal to partial plus partial bar makes it a very elegant formalism. So, but because we've derived the Dolbeau operators through just trying to look at what happens to D on a complex manifold, let's just take stock of what the Dolbeau operators actually are. So there are two operators. Let's say that M is a complex smooth manifold. Then you can define two operators, partial, which it goes from omega pq m to omega p plus 1. See, this is my favorite part where I just have to copy the definition onto the board. So partial bar omega pq m omega p q plus 1 m. So these are our two operators. These are the Dolbeau operators. They're defined by. So we've already defined the exterior product at this point, right? Or the exterior derivative at this point. So we can just say that they're defined by the fact that partial plus partial bar has to equal D. And since they operate on two different spaces, there's only one thing for each of these to do, is to give the two sides of the two parts of D acting on a complex manifold. We also have to define uh, partial f, or yeah, the Dolbeau operator on f is partial f. There's too many partials. There's too many partials right now. Dzj adjoint Dolbeau operator, maybe that's a better name for it, is equal to partial f partial z bar of j dz bar j. Then we have to say that the holomorphic coordinates means these are well defined. So the definition is coordinate independent. So definition is coordinate independent. Okay, so also we define the fact that partial of dzj is equal to 0, partial bar of dzj is equal to 0, partial of dz bar j is equal to 0, and partial bar of dz bar j is equal to 0, which leaves us with omega partial acting on omega would then be there in general would be more terms, right? Because of the Leibniz rule, there would be more terms, but essentially we just get this. Remember, this is just for a complex manifold, but they're only definable on complex manifolds, so I guess that's not a big deal. All right, and so these are, again, these are multi-indices. multi-indices. So, and lastly, they satisfy partial squared equals 0, partial bar squared is equal to 0, and partial after partial bar. I wasn't writing the after before, I guess, so this is the full way to think about it, is equal to 0. So these are the Dolbeau operators. So I could have just wrote all of this at the beginning and then showed that it would work, but I feel like that would be quite unsatisfying. I think it was much nicer to think about D as an operator on an almost complex manifold, and then see what happens when we can impose holomorphic coordinates on it, and then we see that it naturally gives rise to so D on complex manifold naturally gives rise to these things called the Dolbeau operators. And these are going to be really important when we do Dolbeau cohomology. So let's recap what we did today, and we'll do a little preview of what we're going to do next time. So recap. So firstly, we made a little correction that I mistakenly said that complex differential forms, or I left it ambiguous. I said that they were from lambda, or differential k forms, were from lambda k t star m. They're not. They're from gamma of lambda k of t star m, which is by definition omega k of m. So small correction there. The main part, we started with the exterior derivative, and then we said on an almost complex manifold, if we send omega to d omega, then this will be an element of omega pq plus 1 m plus omega p plus 1 q m plus omega p minus 1 q plus 2 m and omega p plus 2 q minus 1 m. And then we saw that on a complex manifold, because of holomorphic coordinates, d omega is just an element of omega p plus 1 q and omega p q plus 1. And that allowed us to decompose D into a very simple form where these are called the Dolbeau operators. And we saw that they satisfied all of these things. We just covered them, so I'm not going to go over all of them, but the important ones were partial square 0, partial square is equal to 0, partial bar squared is equal to 0, and partial after partial bar plus partial bar after partial is equal to 0. So next time, well, we were supposed to do cohomology, this this lecture originally had orientations in it too. I can notice that we're at the 1 hour 4 minute mark. Originally had orientations, which are going to become important because we're going to need to use the fact that almost complex manifolds are always orientable. So next time we're actually going to do orientations and integration. Orientations and integration. Because one of the main interpretations of differential forms is things that or these objects ready to be integrated. They're very linked to integration, and when in regular calculus, when you see this kind of thing, dx, dy, that's actually secretly a differential form. And it's telling you a little area element that that you're integrating over. And then the function there is the coefficient of the differential form. And you're integrating it over a manifold. In that case, the manifold turns out to be R or C, depending on where you're integrating. Well, I guess integrating on C is a lot more complicated, but yeah, in general, R. So we'll look at that. We'll look at orientations and volume forms. So that's another thing that don't have a lot of space to write this. So volume forms. Volume forms have a lot to do with, I think, symplectic manifolds, and so they're going to be important to define something called the Kähler form, which is central to something becoming a Kähler manifold. Just a small preview. A Kähler manifold requires something called the Kähler form, which we call omega, to be a closed form. So d omega is equal to 0. So if the Kähler form is closed, then we get a Kähler manifold. Obviously, this is not a well put statement because we haven't defined a Kähler form. We don't know where a Kähler form lives. So that's why this is just a preview. Sorry. But yeah, just an idea of I'm trying to give you an idea of why all of the stuff that we talked about is important. We'll also need it for Hodge decomposition. The PQ decomposition is going to be needed here. Decomposition, and to even like define Hermitian manifolds. We're going to need forms. Like, forms are the bread and butter of complex differential geometry. So this is why it was so important to talk about complex forms, and why it's going to be necessary to talk about orientations and volume forms as well. So that's it for today. Next time we're going to be talking about orientations and volume and integration, as I said. So goodbye and see you next time.